Guys, welcome. We are week 14. We're looking at lesson 112, 113, and 114 for this week. So those three lessons. Let's go ahead and flip over to 112. So in lesson 112, we're looking at ratios of side lengths of right triangles. So this is kind of jumping a little bit ahead of what you're going to do a lot more when you guys get into trigonometry and covering some of those concepts. So this is just kind of a basic introduction, but it'll be very applicable in things that you guys use continually as you get into high school. So trig, as it's called short, is a branch of mathematics that explores the relationship between the angles and the sides of triangles. We use it in surveying, navigation, engineering. Again, if we can't directly measure something, this is one of those indirect measurements that we can use to very accurately calculate a distance. Some terms that you'll see, opposite side, adjacent side, and then the hypotenuse, which we've talked about already. So when we're talking about these, it's in relation to whatever angle we're talking about. So if we're talking about angle A, that's when we're referencing. The side opposite from it would be length, side length BC. The one adjacent to it is AC, this side right here. Now you may say, well, this side is also adjacent to it, but it is the hypotenuse because it's across from the right angle. So yes, it is adjacent, but for our terminology's sake and for keeping sides straight and knowing which one we're talking about, opposite is across or opposite from the angle. Adjacent is the one obviously closest to it, and that comes to the vertex, and then the hypotenuse is the one across from the right angle. So this works with right triangles. We have opposite, adjacent, and the hypotenuse. So again, if we look at that same triangle but referencing angle B, now this side is opposite, AC is opposite, BC is adjacent, and the hypotenuse remains unchanged. So we're looking at these two triangles, ABC and XYZ, the ratio of angle A to the length of the hypotenuse, and express it as a fraction. So opposite from angle A would be BC, which is 3. Adjacent would be 4, and then the hypotenuse would be 5. And if we want to express that as a fraction, the opposite over the hypotenuse is 3 over 5, or 3 divided by 5, which ends up being 0.6. Now, let's say we scale it by 2, and our 3, 4, 5 right triangle becomes a 6, 8, 10 right triangle. We just multiplied everything by 2, so our dimensions have doubled. Let's look at the relationship. So we're looking at A, now we're looking at X. Okay, the opposite over the hypotenuse, 6 over 10. That also divided or reduced down is 6/10, 0.6. The same thing here. So we can see that that relationship held true because this angle measurement and this one will be the same because these are similar right triangles. So the relationship is going to be similar as well. If we're looking at this triangle over here at the right, find the ratio of the length of the opposite side opposite angle R to the length of the adjacent side. Then use a calculator, find the ratio around 23 decimal places. So angle R, opposite is 1. The adjacent side, maybe we don't know, we could use the Pythagorean theorem to find a squared plus b squared equals c squared. And that would be a squared plus 1 squared, which is 1, equals 2 squared, which is 4. Subtract 1 from both sides, we get 3. So it's a square root of 3 is what it ended up being. So our ratio is a square root of 3 over 3, and then if we divided that, it'd be an irrational number, so we would need to round it. In this case, it would round 0.577. Okay, so biggest thing, and we'll get into sine, cosines, and tangents that we use off of that a little bit. We're not going to get into too much of it this year. You'll do a lot with it in the future. But just understand from our referenced angle, which side is adjacent, which one is opposite, and then the hypotenuse is always across from the right angle, but make sure that you can identify that always. We'll do that practice set together. Should go pretty quick. All right, lesson 113. Yeah. Lesson 113, we're using scatter plots to make predictions. So again, a scatter plot is where we have two things that we're looking at and trying to find if there's any relationship. And sometimes we have things where there may be a correlation. That doesn't necessarily mean causation. So just kind of be aware of that. Sometimes people want to make references to something causing something else, and there may just be a correlation between them, but one isn't necessarily causing the other. So if we're looking at this, a correlation, so if we were to look at this and we do a line of best fit through these points, obviously not through all of them, but a line that would most best take the shape of this graph, it would be obviously a positive correlation, because from left to right it's moving up, it would have a positive slope, so it's positive correlation. From left to right, we're going down, again, this would be negative correlation. Now this one, we could do a horizontal line, a vertical line, an angle, upward diagonal, a downward diagonal. That tells us that there's really no correlation. So the closer it's getting to a line, the better the correlation. The further that's getting apart and looking more like a circle or just scattered everywhere, that's probably telling us that there's no correlation. So if we look here, each student in a science lab receives a specimen of a certain mineral and measures its volume and mass. These measures for each specimen are listed below, and each data point is graphed on the scatter plot. So the volume in cubic centimeters, and then we have the mass in grams. So we have it plotted here, and we see that it looks like the greater the volume, the heavier or the greater the mass. It's going up. It's not perfectly linear, as most things in the real world never are, but we can see that it's trending upward. So if we want to draw a line of best fit, we would probably start in the origin, because if it has no volume, it's probably going to have no mass. And then draw a line that goes not through all of these, but it's going to go through some of them, and it's going to have some above the line and some below the line. And then use that best fit line to predict the mass of a specimen mineral that has 100 cubic centimeters. So our line of best fit would just go through there somewhere. Again, it's not going to hit every point, so they're not directly in line with each other. We would want a line that would be the quote-unquote best fit line. And then to predict, well, we could find some ratios to see. It looks like 2 cubic centimeters is about 5. It looks like 10 is about, up here maybe 28, 29. So we could use some different ones of those. 5 is about 12 or 13. And we can zoom in to see. So in predicting our line of best fit, so again, we go through the origin, so it doesn't have, the y-intercept is the origin. And we go through a point here, here, barely touching this one, and then this one down here. It passes through the origin in 1027, so the slope, rise over run 27 divided by 10, would be 2.7. And there's a way that we can do correlation and line of best fit and linear regression and things like that on the calculator. We may show you a little bit, but it may make things more confusing at this point. All right, so if we have our line of best fit, then we put in 100 for x. Since it's linear, we put in our input and get our output with 2.7, if that's what you had for your slope, times 100 for x. 2.7 times 100 is 270 grams. Okay, so we can use that to make predictions. We're not just guessing, we're not just giving some points and like, oh, I don't know, I guess we'll just call it this. No, we can use a line of best fit to say this trend isn't perfectly linear, but it is, showing a pretty strong relationship positively, we can use that to note, okay, if we had a specimen that was 100 cubic centimeters in volume, we could estimate maybe 280, 250 something, but it's going to be around 270 grams. We can say that pretty confidently. Okay. We may look at that activity, but okay, there is no practice set. So when we get into class, we can show you guys how to do some of this in a calculator. We can make lists versus individual points and then plot that on a stat plot and then go through and graph it. Let's see if I don't think I have one. So we go into list 1 and list 2, and so where we get in there, I don't have an example in front of me to put in there, but what I'm talking about is in this. So we go from our home, if we go stat or list, and then we hit edit, and then we put whatever the values are in two of the lists. I just always use, out of habit, list 1 and list 2, and we're comparing two things. And then we go in and we can use the stat plot if we're looking at, you see it there, but linear regression, then we would use list 1 and list 2, and then we could graph and it would have all of those points, and then there's a way that we can apply a line of best fit to that. So we'll look a little bit more at that when we get to class. All right, and then the last lesson for this week we're going to be looking at is calculating area of a sweep. So a sweep is just like it sounds. If you were, say the floor was covered in paint or dirt or some sort of powder or something, and you swept it away, you would create a clearing where that paint or that substance no longer was. So if we look at this, so the width of the broom, okay, again, keeping it flat on the ground or the surface and pushing it directly forward, well, it's going to create a rectangular area right there. It's not going to be getting wider as it goes or more narrow. The length of the broom is going to be the same no matter where we go. Now imagine we're sweeping an area with one side of the broom kind of place. So we have a pivot point right here, and then we kind of sweep it in this circular motion. The area equals the width of the broom times the average, or the mean, the distance the broom is pushed. We'll apply this concept of sweeping to calculate some areas and surface areas. We start with a circle, then we calculate the outer surface area of a cylinder and a cone. So circles, we worked with these plenty, so this is just going to help us introduce to what we're looking at with a cone. But again, radius CA sweeps through an area of a circle. How wide is the broom CA, the radius? The radius is 5 centimeters. We're given that. So nothing too complex there. How far does point A move in one full turn? Well, we would go point A, if it went all the way around and back, well, that would be one rotation, or that would be the circumference of the circle. So we would do 2 pi r, so that would give us 2 times 3.14 times 5, 31.4, or if we left it in terms of pi, it would be 10 pi. How far does point C move in one turn? Well, that is our pivot point, essentially. That's kind of the stake in the ground. A is moving, but C, that center, it's going to remain there. So C actually does not move at all. And then D, what is the average distance the point from A to C moving during one full turn? To find the average of those, we would add those together. This was C for center, this was A, so all the way around from A, if we started all the way around, that would be the circumference. C isn't moving at all because what do we move? Here, here. Even if we keep doing circle, C is not going to move. That point is our center, and it's going to remain there. We were asked for D, what is the average distance that points from A to C move during one full term? Well, A we just said was 10 pi, and C didn't move at all, so we took the average of those. 10 pi plus 0 is 10 pi divided by 2 gives us 5 pi. So that's the average that it turns, because this turns the circumference. This doesn't move at all, so take basically half of the circumference, 5 pi. That's how much it moves. E, we're asked, the area of the circle is the product of the length of the broom, CA. Okay, so this is where it's getting back to the sweep, and then this is going to tie into finding surface area and lateral surface area of the cone in the middle. So the area of the circle is a product of the length of the broom, CA, and the average distance the points of the broom move. What is the area? So we have the product of the radius and its average distance. So the radius, that's the width of the broom handle, if you can think of it as that. Or not the broom handle, sorry, the broom itself. This is how wide it is, and if we imagine this is a push broom, and we make this point stationary and kind of just do like a swooping circle with our broom, then it's going to travel this far. So we find the average of this length, which is our radius or broom length, which is 5 centimeters, and then the average we just found right here between these two, distance traveled for A and C was 5 pi centimeters. We multiplied 5 times 5 pi, which is 25 pi, and then centimeters times centimeters, it's area. So we have square centimeters. Lateral surface area of a cylinder is represented by the label of the can. It's always your coffee canister, your soup can, or the sanitizing wipes that we have in class. If we think about taking off a label, we're going to have for lateral surface area, we're going to have a rectangle, and it's going to be whatever the height of the actual can or cylinder is, and then the label all the way around would be the circumference of the circle. So circumference times the height, that's going to give us the lateral surface area. And circumference of a circle is 2 pi r, or pi times the diameter, and then height is represented by h. So that's how we can go through in finding those. Now calculate the lateral surface area of the cone. The diameter of the base is 2, the slant height is 4. Radius. Diameter is 2, so the radius is 1, and it's inches, 1 inch. The slant height, which is going up the face of the cone, not the height from the center to the top. So the slant height, we've worked with this with cones and pyramids and things. Think of this as a right triangle right there. So the slant height would be right here, and we're told that that is 4 inches. So we're going to find the surface area, or the lateral surface area. And again, this is on your reference sheet, so you may want to have those handy as you're going through. We talked about volume of the cone, but now we're looking at surface area and lateral surface area. So So we get pi times r, and then our reference sheet uses the cursive L for the slant height, plus pi r squared if, because that's the area of the circle, if we're doing total surface area. If we're just doing lateral surface area, then we don't need to worry about the circular base down here. So pi r times the slant height. The pi, are we told? Okay, we're going to leave in terms of pi. Okay, so we get pi times the radius, which is 1, pi times 1 times the slant height, which is 4. 4 times 1 is 4, so we end up with 4 pi, and then it's lateral surface area. Anytime it's area anything, it's units squared. Or if we wanted to use 3.14, we do 4 times 3.14, which is 12.56. Squared, so that's 2. Okay, so pi r times the slant height. Remember that. I think it's easier for me personally when I start thinking about the sweep, the averages, and that's one way to think of it, and it's kind of a creative way to introduce it. But I think just having the actual formula in front of you and then plugging in the numbers that you provided and calculating it, I think is a little bit easier. So as I mentioned, this is on you guys' reference the key up here again, the difference between B and capital B, and then this cursive L is what we have for slant height over here. Right circular cone, again, we talked about volume. It's a third of a cylinder, so that's what we do, 1/3 times the volume of the cylinder. This, we have all of this, 1/2 times 2 pi r, because we're taking the average. The circumference plus 0 is just the circumference, and then we're dividing it by 2 and multiplying it by 1/2 times the slant height, or easier than that, because the 2 times 1/2 becomes just 1, so it's just pi r times the slant height. If we're doing total surface area, then we also include pi r squared. So if you want to have these written down on your reference sheet, by all means, please do. We can use similar calculations. So again, this is just where it's kind of bringing it all home, talking about the sweep and the slant height. Again, our broom, as we know, can't get smaller, but if we're thinking about it as far as an average and getting smaller, it's going to be the average of the radius and whatever size of the broom head is. That's going to give us the number that we have. But again, for me personally, I think it's easier just to know, okay, circumference divided by 2. The circumference of the circle is 2 pi r, so 2 and 2 cancel out. So pi r times, they're using L for the slant height. Our reference sheet has a little cursive L. Either way, just make sure you know what's being referenced. So if we know the radius and the slant height, pi is a constant, so we just plug it in and solve. And we'll do those practice set problems together. And that is it for this week. We'll get to 115 next week. See you guys in class.